Hello everyone, welcome to our demo. Today we're gonna talk about RDMA on NetFPGA. It is very common that on register day, some of your juniors may come to you and ask the courses that worth taking. So for example, you recommend the computer architecture course, and then you tell this information to Jenny, and then Jenny tells this information to Ben, and Ben tells Jessica to take this course. And finally, Mr. Trojan got the information from Jessica and he decides to take this course. But it is too late and there's no spot for him. So he missed this course because of the popularity of this course. But things will be different if you just give a phone call to Mr. Trojan at the very beginning and he will get this information and register successfully. So this is exactly how RDMA works. Traditional network protocol stack will buffer all the packets from network layer to transportation layer to application layer, but RDMA will skip all the time-consuming process and avoid touching the kernel level, so the data can be transferred directly from one node to the other, so we can get a high throughput and low latency data transfer.
Here, I would like to introduce the socio-economical argument. In modern society, online shopping is one of the most popular activities people would do. Let's say Amazon and eBay. Imagine in Black Friday, many computers need to do data synchronization, and main server need to handle lots of requests. Definitely, it would create tons of workload for CPUs and hosts. Let me give an analogy. Traditional TCP/IP is not designed for high-performance computing, and it hard to support efficient communication. With RDMA on the right side, data would bypass the kernel, lower down the network latency, and largely improve the throughput. The customer would benefit a lot and happy to shopping again because they have a wonderful experience. Here we make a comparison. Because Amazon did a great job, it accounts for nearly 50% online retail market share in the US. Plus, not only Amazon, but also Microsoft Azure and Google Cloud, these data centers also apply RDMA to improve their performance. So, what we do is we design a dual-core multi-threaded network processor to implement RDMA transaction. Zero copy is one of the most attractive features we have, and it reduces greater than 80% on reading and writing time. Here is our timeline.
Okay, next I will talk about the hardware configuration. So our design is based on the RISC-V. So why we use the RISC-V? Because it is an open source instruction set, and its instruction set architecture is simple but very efficient, and it is very suitable to be integrated with FPGA or other self-baked designs. And this is our 5-stage pipeline. We can see if a normal packet comes in, it will follow this data path and do some modification, and it will be dropped to the output queue. And if it is an RDMA packet, some pseudo instruction will cooperate with it, and we can get some exactly part we want, such as the header address. In this picture, we can see our two cores are placed in series, and it is between the input arbiter and the output queue. So our first core is used to identify the RDMA packet, and if it is an RDMA reading, it will remove the middle header. We can say a packet is in the MAC, and it is what the packet look like. And our core 1 will get the RDMA header location, and if it finds it is an RDMA request, it will drop all of the middle headers and put the RDMA header to the hardware register for the future use, and drop the data to the output queue. And our second core is used to adding header when it is the RDMA reading, so the packet is in the CPU. And our core 2 will get this packet, and if it finds it is RDMA reading, it will add the headers in the middle and give the packet to the output queue.
Let me introduce our software driver design. First, we created a proc file in our driver in order to call mmap function at both kernel space and user space, so that we can map a shared memory between user space and kernel space. Then we can use DMA to modify that memory and let user space application to access that memory at the same time. When a write request comes out of the user data path and triggers the interrupt, the driver will determine if it's a normal network packet or an RDMA write request packet by reading the software register. If the incoming packet is an RDMA write request, the driver will send the required information for DMA to the NetFPGA and start the DMA operation, and then NetFPGA can finish the transaction without interference of CPU. If kernel finds the incoming packet is an RDMA read request, the driver will send the request data like address and the length of the data to NetFPGA. Then the driver will start DMA and let NetFPGA fetch the data through DMA by itself. This is our design flow for our DMA operations.
Preparation for testing. In order to facilitate users to use our RDMA system, we create our RDMA API. Any application can call these functions and get access to RDMA functionality. For test, our application is meaning to send to or read from a target a specific length of content by calling our RDMA API. Next, we wrote programs for a server and a client respectively, by which we can send or receive requests or data under traditional UDP protocol. The third is a bash script for setup. We use it to remove the old device driver and insert the new one we designed for our RDMA system in kernel space. We also use it to configure the IP addresses for all of the NetFPGA interfaces and download our pipeline onto NetFPGA. The last is a program to get access to a specific part of memory where we save data for RDMA and check and print out the data in it.
If we use the normal database to write it, after the NIC receives it from node, we start timing. As we can see, the data has to be copied from buffer to buffer. After it reaches the memory in user level, we start timing. The whole process will take about 100 microseconds. If we use RDMA, it will be much more faster. The NIC will send data directly to the memory in user level. It will only take about 20 microseconds. This data we get from memory. It is same with what we send. Similarly, if we use normal user database to read it, after the NIC receives the request from node, we start timing. The request has to be copied from buffer to buffer, and then the user level will send data. The data will also have to be copied from buffer to buffer. The whole process will take about 20 microseconds. It's very long. However, if we use the RDMA to read data, it will be much more faster. After the NIC receives the request from node, we start timing. The whole process is extremely fast. We only need to take about 40 microseconds.
Is a comparison between traditional UDP and our RDMA system. If you only use the UDP protocol to transmit a packet smaller than 1 kilobytes, it may take you nearly 100 microseconds. But if you use our RDMA system, the time will be reduced by more than 80%. If you want to get data back from the server, compared to traditional UDP, our RDMA system will also reduce transmission time by more than 80%. So our RDMA system have great potential in large-scale applications. When you send or receive large amounts of data through our RDMA system, such as syncing various files with the server, you don't have to wait for a long time. RDMA will complete the transfer very quickly. Here, I would like to show you the test process for our RDMA system. The first step is to use our setup bash script. As we can see, the old driver has been removed and the new device driver has been inserted. Also, our pipeline has been downloaded onto the NetFPGA. At first, we use the check function we wrote to print out the data in the specific part of memory. There is no data in it originally. Then we start listening by using TCP-dump2 and send random content through our RDMA system. As it shows, this data has been sent to our destination. We recheck the memory space. The data has been written in it. We type in the message command. It will show the time our RDMA system spent on writing, which is 23 microsecond. Then we read this data back from server through our RDMA system. As TCP dump shows, the data has been sent back from server. And we check the time. It only takes 46 microseconds.